Kia ora everyone. Welcome to today's topic. It is single phase and three phase generation. So, good news on this one. This is not something that has a lot of new information in it. We know about, in particular, single phase generation. We've covered a lot of that before. There's a little bit of stuff in here maybe on three phase generation that'll be new-ish to us. So I'll cover that in a little bit of detail as we get to it. But in general, most of this should be revision, and I'll move through it fairly quickly as ever. We have a 3-digit code for our test on this topic, and the first digit for that code is a 9. The first digit for your test code is a 9. Alright, so generation of alternating current. Alternating current generators are referred to as alternators and are found in many forms. From the type used in most cars as the main electric power supply from the engine to large units driven by water turbines in New Zealand power stations. So essentially every type of generator that we use, other than DC generators which would have a commutator on it, that's the main and most important difference. Everywhere that we get power is some form of alternator. As it says here in a car, your car has a 3-phase alternator in it, and then a rectifying circuit to turn it into DC to power your batteries and power the electrical items in your car and charge the batteries. But essentially at its core it is in fact a AC alternator, so they are really everywhere. And here's our simple AC generator. Now this diagram, we must have seen this 100 times, right? So we should all know this stuff. We have our coil here, that's the blue part in the middle. That's going to turn around and around. We have on the outside 2 magnetic poles. One is north, one is south. As that coil, remember when a conductor moves through a magnetic field, as it moves through that magnetic field, it's going to induce some EMF, it's going to induce a voltage into that coil, which we can then tap off, right? We'll have a negative and a positive side output. The bigger that magnetic field, the greater the voltage that will be produced. And then as we turn that coil inside the magnetic field, remember that as it goes through the strongest part of the magnetic field, we're going to get the greatest voltage generated, so we'll get a peak, and then as it starts to go out of the magnetic field, it'll come down. I'll just make my fingers on the screen in the camera. When it goes out of the magnetic field, when the coil's not in the magnetic field, it'll be at 0, and then as it comes back in, we're going to see it slowly rise and peak again, but on the other side, the negative side, and that's what gives us our sine wave. The sine wave is just describing essentially the coil moving through that magnetic field from outside the magnetic field through the most powerful part of the magnetic field, out of the magnetic field, and then back on the other side again, so we get a nice positive and negative peak and that sine wave that repeats. Remember, we have on our AC generator, we have slip rings as opposed to a commutator on our DC generator. A commutator will keep the output constant on positive and negative. Remember that the rest of the generator, even on DC, is the same, so it does kind of generates AC. It's just that we basically rectify it on the output using a commutator, but it's an AC output. However, on AC, we don't bother with that, so whatever polarity that side of the coil happens to be, that's the polarity that we grab. So we'll show the positive and negative, and it's coming out of our slip rings there. We just have our carbon brushes sitting against the slip rings, so the slip rings can move. These carbon brushes will wear over time, but they're designed to do that. And as they sit against that slip ring, then that gives us the ability to get that power out of that moving out of that moving rotor inside the magnetic field. So when a rotating force is applied to the coil of an AC generator, this forces the coil through a magnetic field of the permanent magnets. This induces an EMF into the coil, which connects to the slip rings, brushes, and supply leads. The slip rings allow the polarity of the output to alternate during the rotation. Exactly as we just said. Where's my hand? Right. And here we have. Just turn the old laser pointer on, there we go. So here, as I described, this is our sine wave output. This is what we get from rotating a coil through a magnetic field. At the start, we would see the we would see the coil being outside the magnetic field. As it moves through the magnetic field to the strongest part of the magnetic field, then the voltage output gets bigger and bigger until it's sitting completely inside the magnetic field at right angles to the magnetic field, and we'll have our highest output. And then as it turns out of the magnetic field, it decreases until it goes through zero again as it comes out of the magnetic field. Now it goes through the other side of the magnetic field on the opposite pole, and we have the same effect, but it's going to be negative. Note here we have 325 positive and negative. That's our peak. That means this is a 230 volt RMS waveform, because 325 will be our peak if 230 volts is our RMS. That's just a good thing to know. And there is the description of each what is happening at each location on our sine wave, right? So 90 degrees is 1/4 of a turn. 90 degrees is literally 1/4 of a turn, right? If I turn my hand 90 degrees, that's 1/4, 180, and so on, and go all the way around. So 90, 180, 270 is here, 360, all this we've done before, right? So I won't read all of those. You can pause the video and read them yourself if you want, but essentially the same as what I've just described. So our simple AC generator has two main parts. We have our stator and our rotor. They interact to generate electricity. Two important laws explaining how they interact are Faraday's law and Lenz's law. The speed of the generator must be kept constant to keep the electrical frequency at 50 Hertz. That's because 50 Hertz is what we use in our normal stuff, right? Our normal AC power output is 50 Hertz for our grid, and therefore all of our appliances and so forth are 50 Hertz. Also, they're designed to operate on 50 Hertz. So that's fine. That's our grid. If you think about it, though, anything else that's generating power or outputting any sort of electricity, AC electricity, would also have to be 50 Hertz. It has to be the same, because that's what all of our appliances are designed on. If you think back to the previous unit, which was special power supplies, that we had generators there, so generating sets, UPSs, that kind of thing. They're all going to have to generate 50 Hertz as well. So we're going to, obviously, when we design and build those things, they have to figure out how to keep that output at 50. Okay, so the rotor rotates and is in the center of the generator. The rotor is on a steel shaft that's connected to the spinning turbine. So the turbine spins. That's the prime mover, right? That's wherever we're getting our mechanical force to turn the generator. So that'll be our water turbine for a hydro dam, or part of the would be the engine in a diesel generator or whatever. We have coils of wire in the magnetic field, and which are created using a DC current. It has sliding connections, which allows DC electricity to enter the rotor. The sliding connections are called slip rings. The stator and the rotor interact with each other through the strong magnetic field between them. Excuse me. How they do this is explained by the following two laws, which are not yet. The stator is stationary and surrounds the rotor. The stator has large coils of wire, the coils that create the voltage and the current when the magnetic field cuts the wires. It has usually 2 or 4 magnetic poles. The number depends on the speed that the rotor spins. We'll look at this later, but the frequency of the output is dependent upon how many times in a minute, or actually how many times in a second we cut that magnetic field, right? So obviously that's dependent on the speed of the rotor, but also dependent on how many windings we have, or how many magnetic poles. Because if I double the amount of magnetic poles, then I'm going to double the number of times that my magnetic field is cut in a second. So I'll double the frequency. So our frequency is dependent on speed and the number of magnetic poles, which are contained within the stator. And here is basic construction of our generator. This is kind of what it looks like. So this is a cutaway here, so we can see the steel cores of the stator, just like a transformer. And then we have a steel core to magnify the magnetism, and just like in a transformer, you can see that they are cut into slices and laminated for exactly the same reason, because we would get eddy currents inside our generator, which we don't want. That's just some wasted power. We have our field windings contained within the within the rotor here. So those are that's the magnetic field that we talk about when we're cutting the magnetic field. So then in the stator we have our conductors. So the field windings create the magnetic field, and then the conductors in the stator are what's cutting the magnetic field. So in this situation, the magnetic field is not stationary with the conductors moving inside it. We actually have the magnetic field is turning and the conductors remain stationary on the outside. It's the same though, we're still going to have the conductors cutting that magnetic field. And here's a little picture of a what do you call it? Water turbine. Which we've seen water turbines before, right? Note how massive this is. We've got a dude down there for scale. So, geez, that looks like it'd be big enough to suck you in and chop you into little pieces without too much trouble at all. So big thing there. And we've got a slightly different looking rotor here because it's kind of big and flat. However, the operation, I can tell you, is exactly the same. So three-phase generation. Now, obviously in New Zealand we use a lot of three-phase power. All our power is generated and transmitted with three phases. It's only really at the final user end, like at your street, that one phase will be taken off the three-phase supply and sent to your house or whatever. So three-phase is actually everywhere. Our whole system is a three-phase system. It's just we don't really see it very often because we don't use that final three-phase product, but we just take one phase off it and that's what we use. But everything is three-phase. So have a look. Here is a little illustration of how that kind of works. So we have a rotor, and we have, instead of just having two poles with one coil, we'll actually have three separate coils. So the rotor is spinning in the center there, and in the stator we have three different coils. We've got a yellow one, a red one, and a blue one in this case. Each of those coils is obviously going to be cutting the magnetic field at a different time, and therefore they're not going to be in phase with each other. And we've seen that, how the sine wave for a three-phase sine wave works, right? As one's coming up, the other two are going down, and so on and so forth. And here it is here. If three single loop turn conductors, so just like this, like the ones we saw in the very first diagram. So when it says single loop turn conductors, that means it's a one turn conductor. It's just instead of having multiple turns, it's a single turn. Rotate in a uniform magnetic field. The EMF induced in those conductors will be three sinusoidal outputs. So sinusoidal means sine wave. Sinusoidal outputs, each one reaching a maximum 120 degrees after the one before. 3 times 120 is 360 degrees, so evenly spaced around a circle. They have to be evenly spaced. So physically, where you put those conductors next to each other in the rotor is what the phase separation would be on our sine wave. Gee, I hope that makes sense. It's a tough one to get across without looking you in the eyes. But if I put all of those three conductors, if I did not separate them 120 degrees around my rotor, then my sine wave output would not be 120 degrees either. If I separated them all by 90 degrees, I'll get 90 degree separated outputs. However, if I space them evenly, three coils on a circle means they will be 120 degrees apart, right? Because if I split 360 degrees up evenly, I'll get evenly three times, I get 120 degrees. And so here's the output here. So what have we got? We've got like one of them is at 0, while the other is at a positive, one is in a negative peak, or not quite. One's almost positive peak, one's almost negative peak, but the total voltage there, you can see the blue is equal to the yellow and the red is 0, so they kind of add up to 0. And if I look here, and I'd see that as those two cross, the yellow one reaches its negative peak. As it starts to come down, then the yellow, the green, as it starts to come down back towards 0, the blue is coming into its negative side and the red is continuing upwards. So again, as we see that peak there of the red phase, the other two are equal and opposite. So we always have the same, essentially the same value above the line as below the line, which is why we don't need a neutral, because at any case, the combined voltage of all three of them is 0. So if I have a positive voltage on one, I'll have an equivalent voltage, negative voltage on the other two. So they'll act as the return path for the positive on on the red one. So they're always acting as each other's neutrals, as long as the load is balanced. Well, in fact, if the load's not balanced, they'll still act as each other's neutrals. You'll just get some weird out-of-phase currents, which we do want to avoid. So, it is possible then to get 3 separate 230 volt supplies from the output of a 3-phase generator. It is also possible to get 3 separate 400 volt supplies from the same electricity supply. The waveforms below illustrate the voltage available between 2 different phases. The neutral is no longer being used as the reference. So as I just said, they're basically each other's neutral. In this example, we've used the voltage of the red phase with respect to the yellow phase, and then referred to that voltage to the x-axis. The speed at which the pair of poles, so the north and south, goes past a point is called the frequency. In New Zealand, the frequency is set at 50 times a second. A lot of effort goes into ensuring that 50 Hz frequency is maintained to ensure all electrical equipment works correctly. Yeah. Keeping the frequency constant. Oh. There's nothing there. Weird. Okay, calculating the frequency. This formula can also be transposed to calculate the number of poles or for the speed. So, calculating the frequency, if we need to go into any more depth on this in terms of the maths, we can cover that in our class time, but at the moment I'll just talk through those formulas there. So if we had a 4-pole generator spinning at 1500 RPMs, the frequency is the number of poles divided by 2, or we could also say the number of pairs of poles, times the speed of the rotor. So in this case, number of poles is 4. It's a 4-pole generator. That means 2 norths and 2 souths is 4 poles. So 4 poles divided by 2, or again, we could say pairs of poles to simplify it. That means we would just go 2 norths, 2 souths, so we've got 2 pairs. Either way, it's 4 divided by 2, which equals 2. And we multiply that by the speed of rotor. So that's 1500 RPM. 1500 RPM divided by 60 will equal the revolutions per second. So 2 times 1500 divided by 60 equals 50 Hertz. So at if I have 4 poles and I spin the rotor at 1500 RPMs, I get 50 Hertz. A 2-pole generator spinning at 3000 RPM. So now I've halved the number of poles but doubled the speed. So it will be number of poles divided by 2 times the speed of the rotor. So 2 divided by 2 is 1. In this case, 2 poles means I have 1 pair of poles. So I could also say pairs of poles is 1. Times 3000 RPM. 3000 divided by 60 will be my revolutions per second. So 1 times 3000 divided by 60, so 1 times 50 will be 50. So we can see there that in either case we get 50 Hertz. That's because our frequency is dependent on the number of poles and the speed of the rotor. So if I half the number of poles, I half my frequency. But if I double my speed, then I double the frequency. If I half the pairs of poles and double the frequency, then I keep the same frequency. And so this is it. This is the standard. We don't use any other numbers. We don't have 1-pole generators spinning at 6000 RPM, because you can't have a 1-pole generator. You have to have at least 2 poles, a north and a south. We could have an 8-pole generator spinning at 750 RPM, or a 16-pole generator spinning at 375 RPM, presumably. Those things might exist, but generally 2 and 4 poles are the number. If we want 50 Hertz, then we just have to stick with that. We can't invent any other numbers. We can't have a 12-pole generator spinning at 2000 RPM. It just doesn't work. The importance of turbine speed then. Well, obviously, I can't change on the fly. I can't really change the number of pairs of poles or the number of poles in my generator. I can't. The number of pairs of poles is how many windings I've installed into my generator. So the idea of changing that doesn't make sense. So the only way to change the frequency output then is to change the speed. Or if you think about that another way, the way to maintain the frequency output, I must maintain the speed. So I don't want to change the frequency, I want to keep the frequency the same. So my challenge then is going to be to keep the speed of my rotor the same all the time. When we talked about generators in the last topic, I talked about governors and voltage regulators and how that relationship works, where the voltage regulator is telling the governor to put more fuel in or take fuel out. As the load changes, it's sensing the change in speed, and what it's trying to do is keep the engine speed precisely at the same speed. And as we alter the load, then we have to change the fuel input into the engine to keep that speed the same. If I take load off the generator, then and I don't change the fuel, then it's going to increase in speed. It's just like if you keep your foot flat, or if you keep your foot in the same place when you're driving your car and you're going up and down hills, then the speed is going to change. As you go down a hill, you take your foot off a bit. As you go up a hill, you put your foot down a little bit to try and keep the same speed. And here is the same. Here is the same. So with a diesel generator, we have a mechanism. We have a mechanism to do that, and it's pretty simple, right? We put more fuel in, take fuel out. As long as we monitor the speed, you have your voltage regulator and governor there that will do that. As the speed drops, we increase the fuel. As the speed increases, we decrease the fuel, and we just keep it hovering in that little zone. In the case of our national grid, we need to keep our frequency monitored much more accurately even than that diesel generator. And then of course we can't control the speed of water flow in our rivers. That will depend on lots of factors, right? In the winter we get a lot more rain, and so there's going to be a lot more water coming down the river than in the summer. So how then do we keep it? How do we keep it the same? So we do it by altering the number of power stations generating and how much is generated from each machine. So that's controlling the load. Obviously, if the load isn't changing, in most cases, we don't need to change the speed. We keep the speed the same if the load is the same. It's only when the load goes up and down I need to then alter the speed of my turbine. So if we alter the number of power stations generating and how much is generated from each machine, then we can try and maintain a fixed load, I guess. Automatic instantaneous continuous control of turbine speed by a governor, and in the case of the diesel generator, I talked about how that would work, how a generator works in that context, or how the governor works in that context, rather. In the case of our large generating facilities, it'll be a little bit different. The governor detects the change in turbine speed with a feedback, so the appropriate adjustment to steam supply is made if it was a steam turbine. For example, if the grid frequency drops, that means if more load comes on and the turbine starts to slow down, then the frequency is going to drop. Then the steam supply on the turbine opens to try and generate more power, to try and let more steam through to keep the speed of the turbine moving at the same. And the opposite also happens. As load comes off the grid, then the frequency, or then the turbines will tend to move a bit faster and the frequency will come up, and so we cut the supply. And it will be the same. So in that case, a steam turbine, but if we were talking about a hydro dam, it would be basically the same. We just control the water supply coming in through the dam, right? So they'll have their, I think if you go back to that previous slide, there was a wicket gate, so that moves to allow more or less water to flow through. In the case of a wind turbine, we control the pitch of the blades. We control the pitch of the blades to speed them up or slow them down in higher or lower winds. Although, in saying that, I don't think that's the primary way that we control the frequency out of a wind turbine. I think there is some internal gearing to keep the generator, generator rotor spinning at the same speed at a variety of different wind speeds. So the windmill itself, or the wind blades, might be turning at different speeds, but we'll get a continuous speed at the rotor, so we'd have some sort of gearing arrangement. I believe that's what happens, because if you have spent any time steering at windmills, and I have, because that kind of thing appeals to me, then you would notice that not all of them are spinning at the same speed all of the time. So we're not controlling we're not getting a continuous speed from the actual windmill itself. So there must be some other way to control the speed internally of the rotor. Anyway, electric power. Power is defined as the rate of doing work. The symbol is P. The unit of power is the watt. The watt symbol for a watt is W. 1 watt of power is produced in an electric circuit when a voltage of 1 volt causes a current of 1 amp to flow. So that should tell us how we calculate power, right? 1 volt, 1 amp equals 1 watt. So voltage times current, 1 volt times 1 amp. Voltage times current equals power. Clever, you know this stuff. It's the simplest maths you'll ever see. We've done way more complicated stuff than that. But why are we talking about it? Because we need to understand the relationship between horsepower and watts. Now this first sentence here, in New Zealand since 1976, horsepower was replaced by watts as the internationally accepted unit of both power and mechanical and electrical machines. Many older electric motors are rated in horsepower. The relationship between these is 1 horsepower equals 746 watts equals 0.746 kilowatts. That's a very telling sentence there, isn't it? It tells us the kind of touchstones that we have for... I'm going to digress a little bit, go on a tangent. You just have to accept it because it's a video. It kind of tells us a little bit about the touchstones of our qualification in our trade, because the reason that I'm talking to you about this is because one of the specific outcomes for this module is to understand and be able to calculate the relationship between horsepower and watts. And why do we need to do that? Well, because in theory, the people who are creating this coil, maintaining this coil, in their minds, we need to know, because we may come across things that are rated in horsepower and things that are rated in watts, and we need to be able to convert between the two. However, I like that we've got the date there, 1976. So that tells me that it's been 44 years. That's even older than I am. Would you believe it? There are things in the world older than me. 44 years that we have been using watts instead of horsepower, and yet it's still seen as a critical part of our qualification to talk about the difference between the two of them. If that doesn't crease your brow a little bit, it certainly does mine. Makes me think, well, is this really? We're not talking about new or interesting things in the electrical trade. No, we want to talk about that thing that happened in 1976, and boy, we better keep telling the apprentices this stuff so they don't get confused. Because apparently you're going to come across 44-year-old motors, and I guess you get all confused and lost if you see that it says horsepower on there instead of kilowatts, and you go, oh, I don't understand what's going on. Bit sad to me. Never mind. There's our formula there. That should be pretty easy, right? 1 horsepower equals 746 watts. That equals 0.746 kilowatts, because 1,000 watts is a kilowatt. Or another way of looking at it is that 1 horsepower is 3/4 of a kilowatt, because 3/4 would be 0.75. So it's pretty close. It's pretty close enough that you can do those calculations in your head, right? So if you did come across a motor that was 1.5 horsepower, for example, then I could go, well, a horsepower is 3/4 of a kilowatt, so 1.5 must be, or something like about 1.2, I guess, 1.2 kilowatts, because 3/4 of a kilowatt is a horsepower. So then if you're replacing it, then you know that you need a motor that is rated at something like 1.2 kilowatts or 1.3 kilowatts. So a little example there, an example of converting horsepower to kilowatts. An electric motor is rated at 1/4 horsepower. What's its power rating in kilowatts? Well, we go 0.25 horsepower times 746 would be 186.5 watts, which would then be, because it does say there, what is the power rating in kilowatts? And always be really conscious of that, because that will trip you up. 186.5 watts is 0.87 or 0.865. We rounded this 0.65, the 65 to 7, so 0.187 kilowatts. Easy. Couldn't be easier. And that's it. That is that whole PowerPoint. That's that module, and we've done it in half an hour. Nice work. I shall leave you there. As ever, if you have any issues, talk to me I will finish giving you the code before I leave. Where is it? Okay, it's 3-digit code. I've already given you the first digit, so third digit, second 2 digits is 23. So first digit plus 23. All right, have a great day.